Hello everyone, welcome to today's POMO Livesolve. So today we'll be discussing the harder end of the test, starting with part 2, number 9, and then we'll go all the way through the end. So there's no definite end time. We'll just finish on once we discuss all the problems. And the problems you can find you can find in this link. So that's penchickomo.repit.app/problems. Let's put that in the chat. So you can open the questionnaire while we do the live solve. Okay. And then if you missed the first live solve, the recording is posted in our new YouTube channel, and also clips for every problem. Okay. So introducing our live solvers for today. So this is in alphabetical order of last name. So we have Cody Briones, Job Dominguez, Mateo Esposha, and Ethan Lo. Okay. So with that, we'll start the live solve now.
Hello, everyone. So I'm going to be doing problem one. So let's read the question already. Let D be a regular deductible. An equilateral triangle with same side length B is placed on every side of B so that it is outside the polygon B. If we connect the vertices of each triangle that are not vertices of the polygon B, we form another regular deductible M. Find the ratio of the area of M to the area of B. So let's first see that we have two regular decagons, right? We have polygon polygon B, regular decagon, and we also regular decagon. So meaning we can simply say that polygon D is similar to polygon N. This will be is it low? Wait, I will try to change my audio real quick. Hello, can you hear me now?
It's a little bit low.
A little bit low. Oh, wait, I will fix it real quick. Sorry. Is it clear now?
Yeah,
Yeah,
we know,
it's
we know.
better. It's better.
Okay, thank you.
Yes,
Sorry
it's
about that.
better.
Thank you. Thank you. So again, I'll recap it again. I'm very sorry for that. So we have two regular dodecagons, polygon B and polygon N. So we can say that polygon D is similar to N. This will be important later on for our problem. So let's continue here. We have that, let's say this is polygon. Let's say we have these sides of polygon B, which is polygon black, right? Then in a regular dodecagon, we have that each interior angle is, we can say that is 180 times 12 minus 2 over 12, which can be simplified to 150. Right? Can someone clarify? So this angle here is 150. Let's name the vertices A, B, and C so that we won't get confused later on. Okay. The So an equilateral triangle with same side length C is placed on every side of B that it is outside the polygon D, right? So this means that there's an equilateral triangle in this side, which is outside, and as well as here, right? This. These are So now we have to connect now the vertices of each triangle that was made here. So this vertices over here. So we will denote as B and E. So now we want to show that to find the ratio of the regular the polygon B, which I will denote here, this side length. Then we also have another regular decagon here. So I should name this point different side. Not B. Because it will confuse you. My bad. So, so now how do you find the ratio of the area of L to D? Using our similarity over here, if two polygons are similar to each other, let's say this is polygon 1, doesn't matter what is, as long as it's similar, super, ganyan. And this one as well, like scaled up, this just also here. Then if they have side lengths that have a ratio of A to B, right? A over B, then the ratio of their areas is equal to A squared over B squared. We will keep this mind later on. Right? Again, A over B is the ratio of the sides, corresponding sides. Then to find the ratio of the area, we have A squared over B squared. So now let's go back to the problem. Now we can try to find the ratio of this length and this length. So to find out, we can try to see what are some angles right now and see if we can try to find some ratios later on. So here, if these are equilateral triangles, we have 60 degrees here and 60 degrees over here. So, and this one is 360. So we have here 360. 360 minus 150, 60 minus 60, instead of parentheses, we have here 90. So this angle that is outside the region D, we have here 90 degrees. Right? So now we have a triangle here. F, B, E. These two lines are equal, right? From the equilateral triangle. So this one is isosceles rectangle which has 45, which have a 40, oh wait, you know your one. So we can try to find the ratio between this length and this length. BF is FE, which is well known that BF over FE over BF is equal to square root of 2. So meaning FE is equal to square root of 2 times of BF. But then we know that BF, again this BF is equal to AB because of course equilateral triangles. So we have here FE is equal to the square root of 2 of AB. So meaning we already found the ratio between AB and FE, which are the sides of the regular decagon. So now using our ratios here, we can say that the ratio of N is to D is equal to FE over AB squared, which is equal to, we can substitute FE, we can cancel out the AB, because here two squared to each other, we have here 2. And that's the answer. So we have here that the answer is letter B. So basically with this problem, so you have to know that when you have two similar polygons, you can try to find the ratio of the areas with their proportion of the sides. And that's about it in this one. We can
Okay.
go to the next problem.
Yeah. Thank you.
Thank
Do
you.
we have any questions for this problem? Okay. So, I forgot to say this a while ago, but we encourage everyone to collaborate in the chat and build up ideas or maybe post your solutions, and we especially encourage people to ask questions if you have any. So with that, let's move on to number 10.
Wait, ako ba dito?
Yeah.
Oh, alright. Okay. What's up, guys? I made this problem, and I think the main solution that I see here when people try to solve this problem is hockey stick, right? Was it 100? Was it 100 choose 2 plus 98 choose 2 plus until 2 choose 2? Was that yeah? So basically, you would just case bash it and just add up the amount of choices for each square, and then you would multiply this by 2. This is most people's solution, I think, but I won't delve into this a bit. I won't delve into this too much, considering this is not actually my intended song. And what I would like you guys to do is think about what it means for a bishop to attack another bishop. So in a chessboard like this, oh, it actually was grid lines already. Um, the motivation for making this problem came to me when I was thinking of bijections, specifically like bijections in a square. And for a bishop to attack each other, they need to be on the same diagonal, right? And what you can think about is, what does a diagonal define? Or like, what defines a diagonal? A diagonal is defined, or a diagonal of a square. A diagonal of a square is just defined by the corners of the square, right? So if two bishops are attacking each other, if they're on the same diagonal, that means um you can connect the two bishops like this. And incidentally, connecting them like this always forms a square. Why? Because the bishop always attacks at the diagonal. And if it's on the same diagonal, then that means you can draw a square with two bishops as the corners. So actually, very neatly, the amount of arrangements wherein two bishops attack each other is just the amount of squares that you can make in a grid. Because if you pick any two corners of a square, like let's pick this square, and we pick two opposite corners, that's actually a unique arrangement of two bishops attacking each other because it's a unique diagonal of the square. So instead of summing all the possible combinations of 100 choose 2 plus 90 choose 2, blah, 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 we can actually just look at the amount of squares um, there are in a 100 by 100 grid. So what would that look like? Well, let's just assume this is 100 by 100. The minimum square, by the way, is a 2 by 2 square, because obviously in a 1 by 1 square, you can only put one bishop. So if we were thinking of the amount of bishops you can put that are right next to each other, like in this diagonal, you're basically asking how many 2 by 2 squares are there in this grid. Because for two bishops to be right next to each other and attacking each other, they would be the corners of 2 by 2 square. So the amount of bishops in this kind of arrangement would be 99 squared, because that's how many 2 by 2 squares there are in a 100 by 100 grid. And obviously you can kind of guess that the amount of bishops that would be like one square apart is equivalent to the amount of 3 by 3 squares they are. And how many 3 by 3 squares are there in a 100 by 100 grid? There should be 98 squared. And if we keep going, there's only like, if the bishops are as far apart as possible, then opposite corners, there would only be 1 squared. And you can kind of guess that this is just the sum of all squares from 1 to 99. But if you think about it in a square like this, there's actually 2 ways to put a bishop. You can either have them in these opposite corners or in these opposite corners, which means you just multiply this sum by 2. And that's an easier way to calculate the total amount of arrangements, I think. And sum this, I think the formula for sums of squares is just mono area under space. The answer would be 2 times 99 times, oh shoot, I forgot, 100 times 199 over 6. And we should be done here. Yeah, so that's a really nice bijection I found while thinking about squares and stuff. Yeah. I don't know the final answer. I am so sorry, guys. But this should be 656 something. All right, that's it.
Okay, thank you. Do we have any questions for this? Okay. If none, we'll move on to number 11.
Hello, everybody. So here is the solution for problem 11. We consider the first equation. So we multiply this by root x, which gives this equation. And then for the second equation, we can multiply both sides by root y, which also gives this. The reason why we would multiply root x to the first equation and root y to the first equation is because of how we see this. In fact, if you add the first and the second equation together, you will get root x plus root y raised to 5 equals to 64 root xy. And for the second equation, if you subtract them, it gives this. Okay, now so so if you take either of the equations, this can be reduced to x equals to 9y. And then if you basically insert this 3 root y plus y raised to 5 equals to 64. No, this is actually 128y pala. Yeah, this is 128 root y pala. So this is, sorry for the mistake. And then we get 4 root y raised to 5, which gives 1024 y squared root y equals to 128. Now solving this gives y squared equals to oh, give me a sec. Let me see if I did this correct. So root x plus root y raised to 5 equals to 64. Okay, so it's supposed to be this. So root x plus root y over root x minus root y raised to 5 equals to 32. Thus, root x plus root y over root x minus root y equals to 2. Thus, if you multiply both sides the numerator and the denominator by root x plus root y, give me a sec to erase. You get x plus y plus 2 root xy all over x minus y equals 2. Okay, thank you, Denise. So we now have this. We now get this equation. And so, transferring the 2x and 2y terms to the other side gives x minus 3y. Okay? Lastly, if you square both equations, we get 4xy. 4xy equals x squared plus 9y squared minus 6xy. Therefore, x equals to 9y. We reject the x equals y case because we can't let x equals y be equal. So now, what remains is we have the following. Okay, so wait, what did I erase? Okay, nothing. So following the x minus 9y condition, we have that 81y squared plus 90y squared plus 5y squared equals to 33 root y. Now, adding all of these together gives 176 y squared equals to 33 root y. And now, 16y squared equals to 3 root y. Therefore, we have y cubed equals to 27 over 256. Thus, the value of y is just cube root of 27 over 256. We can simply substitute this to the x value to get 6561. You correct me if I'm wrong, over 256. There we go.
Yeah, and then you can just compute the things from there, right? So do we have any questions?
Is y cube 27 over 256? It seems that you squared both sides, right? In 16, y squared equals 3 squared of y.
Yes.
Then y is the numerator 27.
Yeah. Okay, wait, let me annotate the process. So 16, okay, 256y raised to 4 equals to 9y, which gives y raised to 3 equals to 9. This is 256, guys. And then thus, y equals to cube root 9 over 256. It's an arithmetic error, so no problem. This is supposed to be 9. And Any more questions? Okay, if no more questions, Kaiser, you can.
Wait. What is the final answer?
Okay, so the final answer is, give me a sec. So, so if y is equal to cube root, then x is equal to cube root 6561 over 256. So essentially 6561 over 9. This is 6561 minus 9 all over 256, which is 6552 over 256. Basically, if it's 6552, yeah, I think you need to use the denominator. Basically, find the last 4 digits of it.
Okay. You're supposed to conclude that the answer is 819 over 32, which is 851.
Yes.
So do we have any other questions?
Yeah. Wait, so the GCD is 8.
Yeah. So anyway, people can do the computation by themselves. I'll just circle the
Okay, done.
answer.
Did right, like I got to 728 y cubed, right? That's x cubed minus y cubed. So what is 728 times 27? No. What is 728 times 9 over 256?
What are you saying again? 720 times 9 over 256?
728. 728 times 9 over 256.
Okay, so the GCD is 8. Basically, this is 32. And then 728 divided by 8, this is 81. So this is 720. Okay, no. Yeah, this is 91 times 9. This is 819 over 32.
Yes, there we go. 819 over 32 is the answer.
Okay. Are we good?
Okay.
Are we good now? Okay. There seems to be no more questions, so let's move on to number 12.
Okay, so let's read the question again for number 12. So ABCD, okay. That ABC is a triangle with sides AB equals to 10, AC equals to 14, and B side BC equals to 16. Point P is chosen uniformly inside triangle ABC. What is the probability that PA is less than PB and PA is less than PP? So I guess for this problem, there was I think you still have to know some definitions to solve this problem. There's like 2 definitions to solve it, right? So one of them, I think some of you already heard of this already, which is about perpendicular bisectors. So let's define first, or see what happens in a perpendicular bisector before we can solve the problem. So I guess in these type of problems, for this for perpendicular bisector, we know that this is 90 degrees here, and this bisects the side length here, the sides here. Let's say the endpoints are A, B, or we can just pick a random point here. So in perpendicular bisector, if a point is on the perpendicular bisector, let's say point Q, right? Then the distance from each of the points here are equal, right? How? Well, of course, that we can use Pythagorean theorem over here. that these lengths are equal and these lengths are equal, then you can use Pythagorean theorem or similarity of triangles to say that AQ is equal to BQ. But how about, let's say, if Q is not on the perpendicular segment, right? Let's say it's closer to A. If it's closer to A, you can definitely see that BQ, length AQ is less than BQ. And this definition will help us to solve the problem so that we can find the probability with these type of conditions here. So now, that's one definition that we can use, that we will use for this problem. And another definition is, in a triangle, I will use the bottom triangle for the fully closed triangle. So I'm going to put this here. I'll just use this here. In a triangle, the perfect the conquer all the perpendicular bisectors from AB, BC, and AC will concur at one point, which is called the circumcenter, which is we do not always as or most of the time O, right? This means that the circumcenter O, if your point is on the circumcenter O, the distance here are all equal from each of the vertices, right? That's one definition that we will that we will focus here. But we're not solely focused on like the circumcenter itself, but how but with the definition we did here, okay, you find this. Okay, so we will line with them. Why is that? Hold on. There's something wrong with your inversion. Why is it on the top? Wait, my bad guys. I will be back. There's something wrong with the whiteboard right now. Is it back? Um, can you wait for a bit, guys? My mirror is lagging right now. I'm very sorry. Okay, it's back now. Okay. Okay. Very sorry, guys, for the delay. I'm very sorry. So again, we will have different type of definition. Two things that we have to use here. The definition of the perpendicular bisector and the figure of the circumcenter, right? So now, let's try to draw. We'll use the second triangle at the bottom. We will try to draw like the circumcenter where it is. I'm not gonna be accurate, so sorry for that. So let's say this is circumcenter O, and let's say we have the midpoint here are D, E, and F. Right? So here's the main point of the problem. What should we do so that PA is the least length, right? if you pick a point, random point here, I will do a speed here, let's say, and I guess it's clear to see that um, that we'll draw first some more lines here on the second center. It's clear to see that point P must be on this area, right? Why is that? Well, let's say um, a point P is not there, and let's say it's over here, right? Let's say point P over here. The thing is, this will make PA longer than PB because of our definition here. It's like um, saying that, because we know that OD, okay, OD is the perpendicular bisector. So if P is near to if point P is near to B, then the length of P is gonna be smaller. So basically, this actually just finds us to solve for these areas, ADO and AFO, over the entire area of the triangle, which is of course probability of um, of ABC. So I think I will not go into deep with the computational stuff here because like there are multiple ways to solve for the areas here. You can try to, let's say, find for the circumradius of ABC with those given lengths, or you can try to just bash with log cosines or whatsoever I did. I think that would be up to you, right? But um, but the main part of this problem is to see how perpendicular bisector works here and about the circumcenter, how they work in a triangle. That's basically the main points for this problem. And eventually, you can try to do the theme of cosines, or try to bash to find the length chase, I guess, with the problems. With the problem with our lengths. Um, and you will eventually get the ADO is equal to uh, fi- uh 55 over 243 AFO is equal to um 49 uh 2 square root 2. And I will just give you a brief on how I got these areas real quick. What I did is try to solve, let's say, um for this angle, which is like I try to solve for, let's say, this is 5, 8. I try to solve for this angle here, then try to um solve for the area of ABC. Then you could length bash it with just the definition is called the angle ABC is equal to angle AOF. Then you can try to solve for the other length. But one can also do to find the circumradius of the triangle. This one. Then try to solve for the areas, then later on solve uh, for the areas of which triangle mentioned. So that's just like a brief case over there. If I try to maybe go on to it, I think it will waste time. So that's I'm very sorry for that. You can try to ask later on about this problem if you have questions later for this problem later. So eventually, um, going back here now, go here with triangle ABC, also 40 is 43. Using our probability here, we have to um, probability of point P inside the point P. Oh no, sorry. Why am I defining that? Very sorry. That was stupid of me. I meant PA. Sorry. Very sorry for the probability part. So PA is the least here is equal to 55 over 2 square 3 plus 49 over 2 square 3 over 40 square root 3. Can simplify this to 52 over square root 3 over 40 over square root 3. Can cancel here. This will multiply together. This will be 13, this will be 10. And eventually, you'll get into 13 over 30 is the answer. Equals to 8. So again, my explanation here is to show how we can try to simplify the problem further with the definition of the perpendicular bisector here and over here. And yeah, that's how you solve problem 12. Any clarifications out there, maybe about the area here, I guess? Or is there no clarification for the community?
There seem to be none.
Seem to be none. I guess we can move on to the next. Thank you.
Yeah. Going back to Ethan.
Okay. Can you scroll down, Kaiser?
No, it's on the right. The next questions are on the right.
Okay.
There.
There we go. Let ABC be a triangle with circumcenter O and angle ABC equals 28 degrees. Let M be the midpoint of BC, and P is not equal to C. Be a point on the circumcircle of ABC such that AP equals AC. If AB equals AM, find angle PMO. The solution is to draw PO and PC. We now connect the lines is okay, PC, and then AO. Because PBAC is cyclic, we have angle ABC equals angle APC is equal to 28 degrees. Also, because AP equals AC, we have angle APC equals angle ACP equals 28 degrees. By definition of isosceles triangles, angle PAC is 124 degrees. Now, the measure of arc PC is 360 degrees. No. 2 times measure PAC is equal to 2 times 124 equals to 248. Now we have arc measure of arc PAC of PA. Okay, measure of arc PAC, which is equal to the measure of angle POC. 360 minus 248 equals to 112. This gives the fact that angle POA is equal to, okay, before proving this, we have MPOC equals to 112. And then angle OPC equals to angle OCP equals to 180 minus 112 over 2. This gives 34 degrees for each. And by the property of isosceles triangles, because OP equals to OA equals to OC, we have angle CAO equals to 28 plus 34 equals to 62 degrees. Wait, it can't be seen. Okay, there we go. Sorry. Now we prove that APOM is cyclic. Over here. So over here, the first thing that comes to mind is proving that either of the opposite angles have a 180-degree sum. That is one of the things. Or proving that either two angles that subtend the same are equal. Mm-hmm. Mm-hmm. Okay, one sec. One sec. So, okay, now we consider the angle measure of BAC. What we do first? Mm-hmm. Actually, let's not. Actually, let's not do that. Instead, we just do this 36 then 28. This is before. Okay. So it is already known that APOM is cyclic. I suppose somebody else can fill that gap in. So that we can get PMO is equal to 62.
Apologies for that. I disconnected, but I'll be resuming the screen sharing right now.
Okay. From the APMO cyclic claim, what we can do to prove this statement is so proving that POA is 180 minus 128 is equal to 120 minus 528. This is 62. Okay. Yeah, it is 62. Wait, why can't I see that one? Okay, there we go. I think somebody can fill in the gap of APOM are concyclic. Okay, now I suppose somebody can fill in this gap. But that's it for the solution.
Okay. Will somebody fill in the gap or we'll go to the next question? Okay.
I don't think anyone is answering right now, so are you open for alternate solutions?
I guess we can come back to this one later. Uh, wait, hold on. Yes, there's a solution posted in the chat. Hold on, guys.
Okay, wait. Can I share screen?
Oh, I'll be the one to share screen.
Okay, sige.
Hold on. Okay, where are we? I guess,
Okay.
yeah, you can
Okay.
now.
Okay. So, um, so this problem again, we read it again. Let ABC be a triangle with circumcenter O and angle ABC is 28 degrees. Let M be the midpoint of BC and P be on a point on the circumcircle such that AP is equal to AC. If AB is equal to AM, find angle PMO. So, let's just try to angle trace and you see if we can find some similar triangles. So we have here, first of all, angle ABM. So angle ABM, I'm basically just reiterating the solution in chat. So if angle ABM is angle ABC is equal to angle APC because cyclic. So anyway, so we have these two angles. And APC. So and additionally, because these two sides are the same, and these two sides are also the same, AP and AC, we have similar triangles from the angles. So we have here triangle ABM is similar to triangle ABC. And so this means this angle is the same as this angle. BAM is equal to angle PAC. Or we can remove this angle right here, angle PAM, to get that these two angles. So we have BAM and PAC, right? And then they share this common angle here. So we can remove that and replace it with, so these two angles also should be the same. So angle BAP is equal to MAC. So finally, we have that. Okay, so again, we have another pair of similar triangles, BAP and MAC from side angle side. So we have the blue side, the green side, and then the angle. Triangle BAP is similar to triangle MAC. So there you go. And because of this, we have that. Actually, no, not too similar. Because they're the exact same, they're congruent. So we have found congruent triangles. And so which means this side, so BP, which is the side opposite the angle, and MC are the same angle. Same side, same side. But M is also the midpoint, so these should be the same also.
So we have PB is equal to BM is equal to MC. Then we just do some angle tracing finally. So PBM is isosceles. So if we so PMB here, wait, okay. Okay, so note that since ABC is equal to, wait, okay. So ABC is equal to 28. So okay, so we have 28, and we can find that angle PAC is equal to 180 degrees minus 28 degrees minus 28 degrees, or equal to 124. So 124 is equal to angle PAC. So angle PAC is equal to 124, and bicyclic with PAC. Yeah, okay. So you have here angle yeah, so which means that this angle is also 124 degrees. Sorry, can I just write it? And so that is 28 degrees again. Oh yeah, so these are the similar triangles. So additionally, PBM is similar to everything here. B, wait, APC. So we have PPM. So this means that this is 28 degrees. BMO, so you have here, okay. Recall, BBC is equal to 124 degrees from cyclic, which means that angle BMP is equal to 28 degrees also. So finally, angle PMO, since a midpoint of a chord, it produces a right angle. So that's a right angle. It's equal to 90 degrees minus this 28-degree angle, or 62 degrees. So if anyone has any questions, you may put them in the chat. So yeah, so we now go to the next question. So we have corrected this question. So instead of least integer value, it has become the greatest integer value. So I don't know, give the mic to Cody.
I believe this is different from the wording things out. But just to get everyone up to speed, where is my pen button? I can't type. Okay, okay. All right. Just to get everyone up to speed, how you would compute um the greatest, or like the exponent of 2 in a factorial is something called legend grace, something. So like how you would compute for 8 factorial is this is equal to what is this equal to? It's to the 7 times 3 squared times 5 times 7. This is the prime factorization of 8 factorial. And what we're interested in right now is getting the exponent of 2. How you would do this is something called this formula, a sort of algorithm, where you'd realize that from 1 to 8, there are 4 numbers of a factor of 2. So you would add 4. And then from 1 to 8, you would realize that there are 2 numbers that are divisible by 4. So you would add 2, and there's one number that's divisible by 8. So plus 1, 7. So this is the sort of algorithm that will get you the exponent of a specific prime factor. In this case, we will get the exponent of 2 by doing this algorithm where we just divide 8 by 2 is equal to 4 times plus 4 divided by 2, which is equal to 2, and then plus 2 divided by 1, 2 divided by 2, which is equal to 1. And for just to check for a equals 100, 100 factorial, the exponent of 2 would be 100 divided by 2, which is 50, plus 50 divided by 2, which is 25, plus the floor of 25 divided by 2, because you realize this is the amount of 50 is the amount of numbers from 1 to 100 that are divisible by 2. 25 is the amount of numbers from 1 to 100 that are divisible by 4. And now we want to get the amount of numbers that are divisible by 8. So you would just divide 25 by 2 and get the floor, which is 12. And then we just keep going. And then we will get that the exponent of 2 in 100 factorial is 97. So 100 factorial will be 2 to the 97 times 3 to the power of 10. So this is for now, this is the only thing we care about. So for the case of a equals 100 and b equals 0, or 100 factorial times 0 factorial, the exponent of 2 would be getting messages. The exponent of 2 would be 97. And let's go back to the question. It's asking what is the greatest integer value of x that can be achieved such that 2 to the x is divisible is a divisor of a factorial b factorial regardless of the choice of a. What this means is that no matter what a b you pick, 2 to the x should divide all of them. This is another way to rephrase it. What is the smallest possible exponent of 2 you can get by a factorial b factorial? Because for the greatest value of x to divide all of them, it should divide them. If that makes sense. All right, so basically we want to minimize the exponent of 2 of a factorial b factorial when a plus b is equal to 100. How you might do this is you might first think of getting just starting at 50 factorial, because that will kind of minimize the amount of 2's. But actually this is not minimal. This would give you 94, 2 to the 94. And obviously that's not in the choices. So we might be able to guess that it's some number close to 50, or it's some numbers close to 50, but not actually 50. And how we might solve this problem is, of course, we might check all of the close numbers to 50, but there's a better way. It's called Coopers, I think. No, Coopers is for juice. But the alternate form of legendaries, which is I'll introduce a new operator or a new symbol. It's called v sub 2. What v2 means is, for example, if we have v2 of 8, that would be equal to 3. What v2 means is the exponent of 2. So 8 obviously is 2 cubed, so v2 of 8 would be equal to 3. And the formula for v2 of a factorial should be, oh shoot, what is it? Yeah, it should be a minus the sum of the digits of a expressed in binary form. So binary is just converting into binary. And how this works is if you have v2 of 8 factorial, we have 8 minus the sum of the digits of a expressed in binary. Well, 8 in binary is just 1, 0, 0, 0. So v2 of 8 factorial will be 8 minus 1 equals 7. And that's correct, actually. So let me start it here. I'm so lost. We want to minimize v2 of a factorial b factorial. And of course, if you add two things together, the exponent is, when you multiply two things together, the exponent is added. So we can think of this as v2 a factorial plus v2 of b factorial. And using our formula earlier, we know that this is equivalent to a plus b minus the sum of the digits of a in binary minus the sum of the digits of b in binary. And of course, we know that a plus b is 100, and we just have to calculate for these now. we just have to calculate for um we want to minimize V2, so we want to maximize what we're subtracting. So let me just replace this with 100. And basically we want to minimize this sum. So how can we minimize the sum, or how can we maximize the sum of the binary digits of A and B? Well, we can look at the binary representation of 100. Just erase everything. Ah. 100 expressed in binary form should be, I should really have like an outline of notes whenever I do this. Wait. 100. Someone help me out. Oh, okay, I got it. Is this right? Is it 1101? Please tell me I'm right. Oh yeah, thank you, Jacob. It is 1101000. And we have two numbers A and B, where if you add them, you get 100. So to maximize the amount of ones, or to maximize the digit sum of A and B, we want as many ones as possible. So to fit as many ones as possible here, you would kind of go for a greedy algorithm, where first let's realize that um, since there is a 1 here, you would have at least 6 digits for both A and B. So let's try to maximize the amount of ones. Here we have 3 zeros in a row. Oh, thank you. Thank you, Penchick. Wait, is that right? Oh, yeah, sorry, it's 100. We see we have 2 zeros in a row here. So to maximize the amount of ones, you would want to carry a 1. So you would want 1, 1, and 1, 0. And then since the 1 over here carries, they would both have to be 0, 0. And again, here we have 2 zeros in a row. So we would want 1, 1, and 1. And the 1 carries, so this has to be a 1. And then we have one last 1 remaining. So we'll just put that anywhere. So that's kind of the maximal amount of ones you can fit into A and B if they sum up to 100. If we count the amount of ones there, that should be 1, 2, 3, 4, 8. Is that 8? Oh, that's 7. So the minimal sum of 100 minus S2A minus S2B should be equal to 100 minus 7, which is equal to 93. Can someone confirm that's the right answer? Actually, not sure. Hi, sir.
Hold on.
I think that's the right answer. So, are there any questions?
Okay, the answer was B. So it's 91, not 93.
Oh no, wait, what did I do wrong? Oh, sorry, Jacob is the right construction in chat. I am so sorry, guys. Um, no, washed. Yes, it should be 101111. And I messed up. I just realized mine doesn't add up to 100 and 011. All right. sorry, I had the completely wrong sum. So you would want to maximize the amount of ones by adding as many ones to possible to one side, then you just fill in the other side with the ones. Okay, that makes a lot more sense. So actually, you would start with yeah, you would start with 6 ones, and then you would fill in the other side with 3 ones. So the answer should be 91. My bad, my bad. Yeah, this is the other equality case. A is equal to 63 and B is equal to 37. And actually that kind of makes sense because you want to minimize A factorial, B factorial, right? And you have 63 and then 37. And if you think about it, if you reach 64, you would be adding 8 exponents of 2. So like heuristically, this should be the optimal case or like the minimal case. So the answer happens when A is equal to 63, B is equal to 37, and there's another equality case, but this makes the most sense. And that should give you an exponent of 91.
Very good now. Do we have any more questions before we move on? Okay, seems like there are none, so Cody, you can continue with 15.
Oh, wait, this is my question. Um, okay, this will probably take a long time to discuss. There's quite a lot of things to back here. But let's just try to understand this question with the m equals 30 case. So if m equals 30, basically asking how many numbers n less than or equal to 30 are there such that 30 divides the summation. Oh, I hate typing on mouse. N to the 9. All right. So you might be thinking, what does it mean for 30 to divide the summation? First, we can re-express this summation as something else, though. This is just equal to a geometric sum of 1 plus n squared all the way to n to the 29, which should just be equal to n to the 30 minus 1 over n minus 1. And it's just asking how many numbers n are there such that 30 divides n to the 30 minus 1 over n minus 1. So let's look at this new sum. We get 30 divides n to the 30 minus 1 over n minus 1, and this implies that 30 divides n to the 30 minus 1. So let's just write that again. And using FLT, if n is co-prime to 30, then n30 should be equal to 130. If n is co-prime to 30. All right? Which means n to the 30 minus 1 should be equivalent to 0, 130. So if n is co-prime to 30, then by FLT, this should satisfy. Is that right? Wait, I legitimately forgot the solution. Oh, yes, yes, yes. Um, it is not mod 30. FLT only works for primes, right?
Yeah, it only works for prime numbers.
Oh, yeah, yeah, sorry, sorry.
Okay.
All right, we're back. I missed a big part of my solution. And using CRT, this basically means that 2, 3, and 5 divide n to the 30 minus 1. So we will have 2 divides n to the 30 minus 1, 3 divides n to the 30 minus 1, and 5 divides n to the 30 minus 1. sorry, I said that. And actually, this is not true for most n, since by FLT n to the hold on. If you check each case individually, we can see that this works because n minus 1 is equal to 0 mod 2 by FLT for coprime n squared minus 1 is equivalent to um 0 mod 3 for coprime n, but n to the 4 minus 1 is actually equal to 0 mod 5 by FLT for coprime n. And we realize that n to the 30 minus 1 does not divide n to the 4 minus 1. So actually 30 does not work, I think. Yeah, it shouldn't work. 30 should not work. And so we can kind of check this for other cases. If we just have to check if the totals of the prime factors of the coprime factors divide the original number. So an example that works would be like 8. And if we do this case for 8 again, we'll have 8 divides n to the 8 minus 1 over n minus 1. And we just have to check the fact that 8 divides n to the 8 minus 1. So that would be oh sorry. By by Euler's totient, we have that the totient of 8 is 4. So n to the 4 minus 1 should be equal to 0 mod 8 because of Euler's totient formula. And we realize that the numbers that should work are are the numbers wherein if you get the LCM of the totents, it divides the original number. Here in 30, the LCM of the totents is 1, 2, 4 is 4, and 4 does not divide 30, so this does not work for most n. But for 8, the totient is 4, which divides 8, so this should work for coprime n. So in general, actually, let's look at a better case. If you look at the case 10, this is asking us if for what numbers of n does n to the 10 minus 1 over n minus 1 divisible by 10, right? Oh, 10 doesn't even work, sorry. Let's do 12. If you look at the m equals 12 case, this is the same question as asking when does 12 divide n to the 12 minus 1 over n minus 1, which is equivalent to asking when does 12 divide n to the 12 minus 1. Not exactly, but we can just look at this right now. And this is the same question as asking when 3 divides n to the 12 minus 1 and 4 divides n to the 12 minus 1. So by FLT, this is true since n squared is equal to 1 mod 3 for coprime n, and n cubed is equal to 1 mod 4 for coprime n. So actually for 12, the numbers that will work are the numbers that are coprime to 12. So for 12, the n that works should be n equals 1, 5, 7, and 11. So there should be 4 numbers for 12 that work. Sorry. Yes. And realize that this is just equal to um totient of um totient of 12. So for numbers wherein the LCM of the totents divides the original number, the amount of n that satisfy it should just be equal to totient of 12. So looking at back at the original question, this does not satisfy um, the condition that the amount of integers is less than quotient of m. So actually, m is a case wherein the amount of n that satisfies it is actually equal to the quotient. An example of a number where this condition is not satisfied is like any prime. For example, we have 11. If you check the number of n less than 11 that satisfy n to the 11 minus 1 equal over n minus 1, the answer should actually be 0 because by FLT, n to the 10 is equal to 1.11 for coprime n. And if you check that, that's obviously not the case. So the condition that we want is for the LCM of the totals to not divide the original number. And we can just bash this for 1 to 30. For 1 to 30, we want the totient or the LCM of the totals to not divide the number. Or we can just count the complementary case actually. The only cases wherein the totient divides the number are this is pretty known 2 to the any number of the form 2 to the a times 3 to the b, where a is greater than 1, I think. So all powers of 2 should work. 2, 4, 6, 9, 8, 16. And then hello, hello. Balik ba ako?
Yeah, we can hear you.
Saglit lang. All right, sorry, I'm back. Anyway, looking back at the conditions, the only m that shouldn't satisfy it, or the m where the LCM of the totals divide the original sum should be, by bashing it, should just be 1, 2, 4, 6, 8, 12, 16, 18, 20, and 24. If you realize we excluded all the primes and every other number where the totient does not divide the original, or the LCM of the totals does not divide the original answer. And we realize these are numbers of like, these are powers of 2, like 2 to the a, or 2 to the a times 3 to the b, and 2 to the a times 5 to the c. Because if you realize, if you get the LCM of the quotients, um, these are all the LCM solutions would be of the form to the A times U to the B times 5 to the C as well. Basically everything, every prime where the totient is a power. So these should work. And actually, all of the numbers here are such numbers. And if we count this, it should be 10. So the answer should be 20. There are 10 numbers where amount of such numbers should be totient of M. And I just realized explaining this question is not it. I did not provide a solution. That should just be it. You just batch out the numbers wherein the totient divides the original number.
Okay. Is it not right? So,
Yeah.
do you have any questions? So again, the answer is 20, right?
Yes, that is 20.
Okay. Let's just highlight that. So now we're done with part 2. Yeah. Okay. We're now done with part 2. We can now move on to part 3. So starting with number 1 again. So these are the 5-point questions. Sige. Start now.
Hello everyone again. So the first question of part 3 is a geometry question. So it says that we have a triangle ABC, and then we have 3 diameters, and you want to find the area of this hexagon that I've already drawn here. So a lot of people actually got this correct. So uh, the answer here is uh, the answer here is twice the area of ABC, or 168. You can kind of look at this and see that these shapes can kind of be folded in to create the original triangle. So uh yeah, if you want to um actually show this, you can either just find the lengths, um so like using trigonometry or some other method, you can find the areas of these 3 triangles, but I'll show another way. Yeah. So yeah, first of all, so I'll just introduce um a config that will help us prove this. So I'm gonna write in the right side of this board. right side of this figure. So if we have a circle and we have a triangle here with vertices A, B, C, and we have the orthocenter here, and we have a parallelogram. So let's say like this. Um, so if you create a parallelogram for BHC, this point is so let's say that's um P. So this point is actually in not only on the circle, but also a diameter. This is a diameter of the circle. Uh, okay. So if you know second quadrilaterals, the opposite side. Yeah, I already said this before. Opposite angles of a second quadrilateral add up to 180 degrees. So okay. Anyway, so first of all, what's angle BHC? So if we just have the altitudes real quick. This one here. So this is so okay. So I'm just gonna call these angles ABC. So this is angle C. So this is 90 minus C, and this one is also. Oh wait, never mind. Wait, we're gonna do that. We're gonna do this. So here's another way. So this is angle A, right? So we have angle A here, and this is a quadrilateral. So this is 180 minus A. So by vertical angles, this is also 180 minus A. And since this is a parallelogram, BHCP, we're gonna have this as also 180 minus A. So we have here the two angles are opposite to each other and add up to 180 degrees. So we have P lies on the circle. Next step is to prove that AP is a diameter. So to prove that, we just need to show that this is a right angle. This is a right angle. Because if you prove that's a right angle, this is a diameter already. So okay, so since this is a parallelogram, this angle here is the same as this angle here. And we know that this is angle B, and we have this is a right angle. So that's 90 minus B. And we have this to be 90 minus B also. So just adding them up, we get 90 degrees. So then this is a diameter. So how can we use the fact that if we have a diameter AP, we create a parallelogram with the orthocenter H. So this is a fun thing to explore. Another thing to explore is that okay, so P is the reflection of H to the midpoint of BC. Another thing to explore is that if you reflect H of the side BC, it's gonna land on the circumcircle also. So here. Anyway, so let's go back here. So in this original diagram, if we have H, the orthocenter, we have three sets of parallelograms. So we have AHBC prime here, AHCB prime here, and HBCA prime here. And because they're parallelograms, these are parallelograms. This triangle here is the same as this triangle right here. They have the same area, and they're congruent. They're congruent triangles, so they have the same area. Next one is these two triangles here are also the same area. Finally, these two triangles here have the same area. So there we go. Wait, actually, I'll label these with that's 1, 1, 2, 2, 3, 3. And so we basically just split the triangle up and just reflected it, made parallelogram. So the hexagon, the total area of the hexagon is just twice the area of the area of the triangle. So if you have any questions, just put in chat na lang. So yeah, that's it for problem 1.
Okay, do we have any questions for number 1? Yeah, I think people can meta solve this by considering like a ABC like solving the problem where ABC is equilateral and then guess that it's twice the area. But here we present the actual solution. Do you have any questions? If none, let's go to number 2. Oh, yeah, it's the special triangle. So 13, 14, 15 has height 12. So the so that's the height to the side with length 14. Okay. Let's move on to okay. Let's move on to number 2.
Okay, so this problem, I guess, yeah, when we just made this problem, kind of expected for a lot of people to um solve here. I think most people would just bash this with Vietas. I guess if you try to, let's say, try to bash it with Vietas here, you can try to find, if there's some of the art types here and whatsoever, right? But I will, let's say, present a different type of solution here, which will minimize the bashing part for this problem. So let's, uh, oh, wait, I think my mirror crashed out again. Okay, I'm very sorry. I will go back here. Okay, I think it's back now. Let's see. Sorry again for the delay. I think my mirror keeps crashing. Don't know why. Okay, we're back. Okay, so for this problem, I will present one solution here. That we can use here. Um, one thing that we can use is algebraic substitution. Um, I don't like dealing with with variables with higher powers, right? R cubed, S cubed, to the power of 46 or whatsoever. So maybe is there something we can do to make that variable R cubed into something linear or maybe even possible constant or probably linear here with the given condition of the roots over here, right? If this is possible. So what we can do is we can check x squared plus 2x plus 5 is equal to 0. And we can, there are two ways that you can try to get x cubed here. One way is to isolate x squared. We have your negative 2x now, minus 5. We transfer the other side. Then we can multiply here both sides by x and can get x cubed is equal to negative 2 x squared minus 5x and let's take this go to x minus 5 using this one this for we can try to substitute x squared with a linear term And we will get this into x squared, x cubed, sorry, equals to negative 2 times negative 2x minus 5 uh, minus 5x. This will cancel out to 4x squared to be negative 10. This will be 10 minus x, if I'm not mistaken. So in this one, so we actually translates x cubed into a linear term with the given conditions. So what we can say now is r cubed is equal to 10 minus r, and s cubed is equal to 10 minus s. So now this makes it easier now to solve the problem without needing the r cube or the higher powers anymore. So we have here now, we can just substitute. We have here 10 minus r plus s. And we have here 1 over 10 minus s plus r. Then we can try to mention, we can try to uh, equal to r 10 minus r minus 2, the quantity of r minus 1, and plus over 10 plus the quantity of r minus plus. This reminds us of cross multiply. And you have here, this will cancel out on the top, so you have here 20 on the top over 100. Oh, sorry, let's go 100 minus r minus s squared. So now this problem will just now wants us to find the value of r minus s. And one thing we can do is we can see that from the given conditions we have task. We have r plus s equals to negative 2, then rs is equal to 5. We can try to square r plus s into r plus s. This would be, sorry, this would be negative 2 squared of quantity I will be 4. This would be r squared plus 2rs plus s squared. What we can do is subtract 4 minus s here, right? Then we can also subtract rs in terms of the numerical value. We have to be negative 4 times 5 will be 20 here. This side will be equal to r minus s squared. So we'll have here negative 16 is equal to r minus quantity of r minus s squared. So this basically will just solve the problem now into 20, the substitute, and minus 100 minus negative 16, which is equal to 20 over 116, which can simply be simplified to 5 over 9. Right? Oh, then sum the numerator and denominator will be here. 79 is equal to 30.
Okay.
So this problem will sorry, Kaiser.
Yeah, you can go on.
Sorry. Okay. So I guess this problem shows uh, uh how algebraic substitution can try to help you simplify higher powers into smaller powers.
Yeah.
So yeah, we will go to the next one.
Okay. Do you have any questions?
Please.
Yeah. You can use pure Vietas here. It just takes a bit more time, but it's not that tedious. Someone here also said like you can just solve for RNS. Yeah, you can also do that. So if we have no more questions, we'll move on to number 3.
Okay, so for number 3, this is actually one of my favorite problems in this problem set. So let's see the problem. Bookmark has the number 1. He proceeds to generate a number by a preceding digit that is either double or half the previous. Of course, she only half if this is an even digit, and she's not allowed to double a digit if it results for in a two-digit number. Also, no two adjacent digits can be identical. He wants to repeat the process until he generates a 10-digit number. The probability bookmark 10-digit number has an even digit sum is m over n, where m and n are relatively positive integers. So let's find m plus n. Um, so for this problem, we can see what let's fill the problem first. So we can start here. We have 1. Right? Let's just have an example here on how it works. Right? We have 1. You cannot divide it. You cannot half it because it's odd, an odd number. You can 2. If you go 2, then you can let's say go 4. Then you can go 8. But you have to half the next one because 8 times 2 is 16. Right? Of course, which is not possible. Okay, that's a two-digit number. This will be back to 4. This will be, let's say, 2, 1, then back to 2, 4. There'll be numbers left. Let's say 4, 8. That would be 5. That would be 10 digits, right? Okay. So this is an example of a possible 10-digit number that bookmark has, right? But seeing that we need the bookmark 10-digit number to be an even digit sum, this will simplify the problem that we need even number of ones, right? We are going we need even number or number or 10-digit numbers. We even number of the digit 1. All right. And when dealing with this problem, I think when you're, let's say, trying to feel the problem, you can actually see that this would be recursion or recursive, basic, somewhat like that. So, and when I do, recursion, I usually do it in a tree diagram. For example, 1, ever, 3, 4, ganyan. Just an example. That's not really the recursiveness. But when you're doing like a tree diagram, at least you try to define what the branches mean if you're going up or going down. Right? So let's define that here. One thing that we can define here is, let's say, if going up, let's say for number n, it's like a piecewise function actually. If you go up, like if the branch is going up, this will mean multiplied by you will twice the number. So, but if it's going down, this will go down the number. Okay? So using that, we can try to, let's say, create a tree to, let's see what are the possible 10-digit numbers later on. So create that tree right now. This might take a long time. Let's say start with 1. This is always the first digit. So let's draw 1. But there's also instances what there's only one line. For example, if you have, let's say, a number 1, you cannot divide it, right? That would be 1/2. So meaning it can only go straight or be multiplied by 2. Similarly, for 8, it can only be divisible by, it can only divide by 3. So you multiply it, it will go it will go to a two-digit number. Oh, four. Wow, that was wrong. Okay, so we can try to create it in a graph that can help us solve the problem. Okay, so starting with the first digit here, we start here. The second digit here will be 2. Going up, we have 4, then we have 1. Then, wait, might be new to the. I think this problem is really badly, I guess, in some terms. So 1, 2, 4, 1. You go up here 8. And what I like to do with this graph is try to combine it if there's common term or two branches. For example, 2 here. This one is 4. Then go down to 1. And this will have a branch. It will have this type of branch that we have here. Right? 4, 1, 2, 8. How many numbers is that? 1, 2, 3, 4, 8. Okay, 2 ones. Go down. 1, 3, 4. Then last one, right? 8. And 30. So this is from not this again. This will be not the first digit. 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. This will be the first digit, and this would be the 10th digit. Right? So we basically made a graph of this already. And first, we can try to find first the total number of where is it here? We can try to find the total number of possible bookmark 10 digit numbers. So we can do that with in counting. We have 1 here, then 1. I call it red, but it not means the power, okay? It means the number of ways, right? We can go 1 here, go 1 here, goes 1 here, then goes 2, then go 1. Why 2 here? Because we add 1 possible way and 1 possible way here. Okay, that's how it works. So here 3, 2, 5, 2. So notice how the numbers actually look like trigonometry. I think some people will already see that. Then if you check what the numbers are. 13, 8, then down here, 21. It will be 21 on top, and then 34. So now we just have to count these totals. Meaning the total will be 21 plus 34, which is 55. So, can I move this down? Or do you think that? I'll move it on the left side. There were, so now we will find now possible, right? Possible can be number. So when I counted this might be, I think some people would efficient way. Very sorry, it's not an efficient way. There are people who do this not an efficient way, but I would try to do how I solve this. So we can start here that we can pick, of course, this would always be the first number. Right? We only focus on the digit 1, right? We need even number of digit 1. So we have 2 cases. We can either pick only 1 here, right? Also, because this is always guaranteed. The first digit, the digit 1, is guaranteed. So it's either you choose 1 of any of these, or one of any of these, or you choose 3 of them, right? You can choose these 3, or you can choose these 3 if it's possible, if it is possible. So I think we will go, I guess, case by case. And I think some people would also try to start case here. This was probably take a bit long, so we will count it. I will introduce you to the different colors. The colors will continue. It must go one, one. It must go to the next number, right? So it goes down here. One, one. I think this is just counting now. So two here, four, four here. Did I count it right? Oh no, I counted wrong. Sorry. Oh, my bad. I thought one here, one here. Then two, two and two here. Then four, then four and four. So count the sum of these ones. We have here eight. Yes. Okay. Then next case again. Yeah. Um. Then instead of choosing this one now, you can choose the other one here. So again, put two again here. I think like um once you try to bash it, it will actually feel it will not feel too long if you know how it works, like how the graph works. So I think once you like try to bash this already, this would be easy. This would be it won't be confusing if if this thing. Um and one here. I'll continue, okay? It might take a long time, but I feel like if I continue, it should take a lot of time. Or let's see. But eventually, I think this would try to find the possible cases for this problem, even with the probability of that thing will happen. I'll stop talking and continue to find the number of cases. Two here, two, oh, no, one. Four. Then I think I already did it in advance, like for others. I think if you try to check here, you check here, you, you can go, like for example, you check now here as well. For this one, another one. You can go up here and down here, so you can actually go down. Then what about the two, 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 the four. Again, so this would be eight to four, then three. On my note, it says for the last case here, that would be four, one, one, two, two, four, two, two, four down here, four down here. Yeah, it will be four. So now, those are the cases if you pick one in between, right? Then for the other case, I will probably erase some of the numbers here already because it might be a bit no what I think this would be like a bit confusing to see these different types of colors and numbers. I will just erase some of them. I will fix here for the other cases now. Okay, next one. This will be let's try three cases. Is it possible to get these numbers? Okay, we'll try this one. So we go one, 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 no, one, go one, um 1, 1, 1, 1, 1, 1. Not taking that's how you solve it. So that's good. Okay, I think that's right. So we go plus 2. You have your two choices there. Then, yeah. Then, let's say for another case of numbers here. Check this one maybe and see what happens here. You go 1, 1, 1, 1. You go up here. Goes you go up here now. Goes up down here. So that's only one way, right? You go like this, but there's only one way. So I'm pretty sure there's one way there. Oh, wait. The graph seems to be missing. Then check other cases if there's possible. Like if we start now, if we skip the first bit, digit one here, then we will continue here. Then we will try to count in a different column. I'm very for that confusion here. 1, 1, 1, 1 down here, continue, continue here, 1, 1, W1 here, one way for that case. Then, oh, I don't know, did I make something? So, let me check what that. Did I miss something? Down here. Hmm. Did I miss something? The answer is supposed to be 12. Yeah, there's supposed to be one more case. I'm missing it, or I might have counted it wrongly already. I'll double check. Before it's oh wait, okay. I think it's one case. Yeah, I did this one case. Here. Yeah, I did. I think I did. I saw the screen. If I didn't start with this digit and I started with if I go let's say if I started with this digit with the first one, then I skip this one. I skip the other one. This will be one put off here. Or did I do this already? Or not I did. Hmm. Okay. I feel like I tried to solve it right now as well. So I'm very sorry. It takes a long time. Oh yeah, I did miss one case. Another one. Yeah, I'm very sorry. It was this case. There's only one way. You can go one, here, you go down here. Then eventually you get only one case. So yeah. So basically, I think with this problem, you'll get you'll have to. I think there's a better way to bash it. And so the total here will be 55. So the probability would be 25 over 5, 55 equal to 5 over 11. So yeah, that is the answer here. So 5 plus 11 is equal to 16.
Okay. Thank you. Before we move on, I'll just say that we'll only do until number 4, and then after that we'll just post separate video solutions for 5 to 8. And yeah. So because if we continue until the end, we might end at like 10 or 11. So let's go with number 4.
Okay, you guys hear me? Okay,
I can hear you.
so this is a one of those one of those problems where it looks really hard. So what a lot of people did was to divide by b to get something in terms of a over b. So I'll just skip to the nicer solution. So uh um I wonder how many people have seen this, but let m let ideally we want only one letter at the denominator. So let m be 3a plus b and n be 2a plus 3b. So we can solve for a and b. So a is equal to this is 7. So it's 3m minus n over 7. And b is equal to 2m. Wait, 3n is 6a. So it's 3n minus 2m over 7. Yeah, someone verify this is correct, but I'm pretty sure this is correct. So if we calculate 9b minus a, this so this is equal to um wait 9b 27n minus 18m plus minus 3m plus n over 7, or 4n minus 3m. Tapos similarly, 4a minus b is equal to 2m. Wait. So there's 2m and then minus n. So yeah, so and then so if we substitute it back, we get 4n minus 3m over m plus negative n plus 2m over n. 4n over m. Wait. 4n over m, yeah. Plus 2m over n minus 4. As you see, this is more easier to deal with. And if, okay, so then by AMGM, so AMGM, so we have, says that a plus b is greater than or equal to 2 times the square root of ab. So this overall thing is greater than or equal to 2 times the square root of 8 minus 4, because 8 is 4 times 2, or 4 square root of 2 minus 4, which is where we got the 424.
Okay. That's it. Do you have any questions for 3 and 4? Okay, I guess we have none. So, thank you guys for staying until the end. But before we end, we first have closing remarks. Denise?
All right. Hi, guys. In case you don't know me yet, my name is Denise Phoebe Chua. I am one of the problem setters of the Penchick Online Math Olympiad 1, or POMO 1, and I also run the POMO Facebook page for my little Penchicks. But as we close today's live solving session, I'd like to address the real reason why we're here today. Maybe some of you saw our email invitation. Yeah, And maybe some of you saw our Facebook post or our Discord, but I'm sure a majority of us are here today because we joined POMO. We are the contestants. And we've said your names, distinction, merit, credit awardees. We've sent your scores through emails already, and we told you which problems you got right, which problems you got wrong, all of that. And with this, some of you may be really happy. You got an award, got a high score, but some of you, maybe you had a different experience. But in the end, that's fine, because, well, nowadays, many contestants forget what math competitions are truly about. Oh, I need to be the champion in this competition. I need to get a medal. I need to get a score of 23 or it's over for me. But maybe it's not always about the awards or not about the infinite Penchick race to become like the best of the best in math. You know, as I've said, I'm here to address the real reason why we're here today. For all the POMO contestants watching this, well, wherever you are, let us remember that we're here for the math, the fun of math. And we're showing you the solutions live so that you can enjoy the math problems and learn math from them. Well, I hope that, well, whether you're leaving this meeting with a certificate or not, we're super duper glad that you showed up in our first ever POMO round. We're just a bunch of high school students, just like you. So we truly appreciate your support for our initiative to prepare students for the PMO and other similar math competitions. Once again, like thanks everyone, and may the penchicks of POMO smile upon you.
Ayun, thank you, Denise. Just saying there's also POMO 2. So if you weren't able to qualify for POMO area stage here, you can join that one. We will disclose the date later on. Yeah. Okay. So a few announcements. Please fill out the following feedback form for POMO 1 and this live solve. If you only joined this live solve, oh, don't leave yet. If you only joined this live solve, you feel free to only rate the live solve. Other announcements, again, we will post the recordings of this session again to our YouTube channel, which is at Penchick along with clips for every problem. We already did that for the first live solve. And we will also post the answer key for POMO 1 sometime after the session ends, maybe tomorrow. Okay. And yeah, again, all of you must have received your scores by now if you participated in POMO 1. If you didn't, please email us with your POMO username and email. And again, we encourage everyone to join POMO 2, especially those who did not qualify for the POMO final stage. And lastly, if you have any questions, don't hesitate to email us. Okay. So, waiting room. Okay. So I guess that's it. Thank you to